Hey, in the last video we took a look at the Laplace transform of e to the I omega t. That was really nice because I know that that was just cosine t plus I times cosine omega t plus I times sine omega t. And we proved that Laplace transforms will preserve the real and the imaginary parts. So the real part here is just the Laplace transform of cosine omega t, and the imaginary part here is just the Laplace transform of sine omega t. That was very, very nice. I mentioned, however, that we couldn't use Formula 1 because at the time we derived it, we were assuming that a was a real number, and we got this restriction that s had to be bigger than a. And that doesn't make sense in the complex numbers. The notions of less than and greater than only make sense in the real numbers, and they don't extend to the complex numbers. But if I remember where that came from, that was making sure that we were going to get an integral that converges. So what I'd like to do is just take a look at the Laplace transform of e to the a plus bi times t. So replacing a real number a with an arbitrary complex number here, and see what the restrictions are on s that will guarantee that we get something that is convergent. In this particular case, we simply have that a was 0 and b was omega. Okay? And hopefully we'll be able to confirm that the restriction here is that s would have to be bigger than or equal to 0. Sorry, strictly bigger than 0. So this is supposed to be the integral from 0 to infinity of e to the a plus bi times t, e to the negative st dt. Okay. So that's the integral from 0 to infinity, e to the at plus, I'm just going to put the I first, I times bt times e to the negative st dt. And that's the integral from 0 to infinity of e to the, now I know I can just combine all of these exponents, because when I'm multiplying I would just add the exponents. This is real, and this is real. Because remember, our variables t and s, we're not allowing them to take on complex values. Okay? So I'm going to get e to the at minus st plus I times bt dt. And that's the integral from 0 to infinity, e to the a minus s times t, e to the I times bt dt. Just separating it now, e to the real part, e to the I times the imaginary part. Now I know that this is cosine bt plus I times sine bt. Okay. And so therefore I know that it's bounded. So this piece doesn't go off to plus or minus infinity. If this is going to converge, I need this to be a negative power of a negative multiple of t. That way, as we go off to infinity, this is going to be a big negative number, so it's going to go to 0. And if I can make that piece go to 0 and this piece is bounded, the whole thing will be bounded. So basically, in order for that to be negative, I need a minus s to be less than 0. So I need a to be less than s, or equivalently s to be bigger than a. Now, if I have a real number, there's just no bi, and I got s has to be bigger than a. But now this is just saying that s has to be bigger than the real part of a plus bi. So if I have a complex number, in order to get an integral that converges, I simply need s to be bigger than the real part of that. Well, notice here, the real part of I omega is 0. S had to be bigger than 0. Okay. So it turns out that I can actually use Formula 1 for complex exponentials if s is bigger than the real part of this multiple. So I can allow this to be a complex number as long as s is bigger than the real part of the complex numbers, I'm going to get a convergent integral. And then the work that we did in deriving that formula is going to be exactly the same. Okay, so we can extend to allow a to be complex. Let's say we were to let a equal, I'm just going to write capital A plus bi. Then what we would need is that s has to be bigger than a, which is the real part of a. Okay. If we do that, now this formula will work for complex numbers as well. Now, I reserve the right on exams to ask you to derive the formulas for sine and cosines without using Formula 1. Because I'm about to do it now using Formula 1, and it's just too easy. It's so nice. But I wanted to make sure that you understood that inequalities don't apply to complex numbers. They do, however, apply to real numbers, and the real and imaginary parts of a complex number are real. So if I wanted to extend this formula to complex numbers, I needed to look at what restrictions on s would guarantee that I had a convergent integral. Turns out it's just that s has to be bigger than the real part. And so for a purely imaginary multiple of t, that just means that s has to be bigger than 0. Okay. Now, with this, if I take the Laplace transform of e to the I omega t, now that's in the position of a, so this is just supposed to be 1 over s minus a. Oops, sorry, 1 over s minus, let's plug in I omega for a, and let's simplify that. So I would multiply by 1 in the form of the complex conjugate over itself. That's going to give me s plus I omega on top. On bottom, I'm going to get s squared. Outsides and insides cancel. Minus I squared is minus negative 1, so plus 1 times omega squared. Oh my goodness, that's s over s squared plus omega squared plus I times omega over s squared plus omega squared. Super nice. It works. We get the right formula. Okay. Again, if I ask you to derive the Laplace transforms for sine and cosine, I will probably say that you can use the method of your choice that doesn't involve simply plugging into Formula 1, just because that's so simple. Okay. But kind of nice to see that it works. Important to understand, though, how we have to check for what is the restriction on s. And it turns out if you've got e to a purely imaginary power, it will always be that s is bigger than 0. If you've got e to a complex multiple of t, s just has to be bigger than whatever the real part of that complex number is. That's consistent with this. If a was a real number, a is the real part of itself. Okay, kind of neat to see.